Today's topic is going to be about making an advanced PDF reader. And I don't know about you guys, but my first impression when I heard about having to make this feature, I was like, it sounds boring. Like PDF readers, who cares about PDF readers, right? But it turned out to be actually quite creative and quite fun to work with. Then I thought it sounds too complex. I thought about the PDF file format and that I have to learn about that and how to parse it and all that shit. But actually it turned out to be simpler than that. And I thought about that it sounded simple as well, that it's just about displaying a list of pages in a list, right? And how complicated can it be? Turned out to be more complex than it sounds like. And the reason I'm calling this advanced is because when you search online for PDF readers in Compose, you'll find a bunch of articles talking about this. But they all have something in common, which is they lack the implementation of how you properly zoom on all the pages at once. Basically, all the articles, what they do is, for zooming in, you have to select one page, and you can only zoom in on that page only. But we know from our experience, like the usual PDF readers, you just zoom in and all the pages zoom in, right? So they all lack this fundamental aspect to the reader. And from my own exploration of this, I found out that actually that is where most of the complexity actually stems from, is that advanced zooming. And this is why I'm calling it advanced as opposed to the basic guides you find online. And as you will see shortly, the problem is less of a PDF reader problem and more of a zoomable image list problem. And you will see that in a minute, okay? But before, let's start with what is a PDF reader to begin with, right? It's basically a piece of software that takes an input, which is a PDF file, and it outputs a set of features that we all know. First is rendering the pages on the screen. Then the users need to be able to zoom in and out. Then they should also be able to scroll and pan. And these three features are the ones we will focus on this talk mainly. But there's also two other features that I'm sure all of you know. Like I have no doubt that you all know about Garhes and linear stock features, right? Yes. Right? But we will talk about those two briefly. And before we dive into the implementation details, let's ask ourselves, why even make a custom PDF reader? We already have a way to show PDFs. We can just put it in an intent and then send it to the system, and the system will select an app to show the PDF file, right? But then what if you wanted to have an in-app experience? Then this solution doesn't fit. But then you could ask yourself, surely there must have been some third-party libraries that do this job for us, right? Someone must have made this. And there are actually a bunch of them. There is free and there is paid third-party dependencies. But what if you don't want third-party dependencies in your project, right? Maybe you have a constraint from the client or from yourself. Maybe the libraries aren't so trustworthy, and how long will they be maintained for and stuff like that, right? You could have these kind of concerns. But then how about Google? Have they developed a first-party library for showing PDFs in-app? Yeah, well, when we started building this, they did not have this kind of solution. But after 3 months, they came out with it, and they came out with the PDF viewer, and it is available for people to use. It's in alpha right now, not fully stable, but it works. However, it's written in fragments, not in Compose, right? And so if you want your app to stay fully in Compose, then this is not the way to go. So for these three main reasons, you might consider creating your own custom PDF reader. Now, we talked about a set of features, and first of all was rendering. So let's dive into that. Now, with rendering, what I first imagined before I started this was that I would have an input, which is a file, and the desired output, which is stuff on the screen, right? And in between the input and the output, I would have to go through a bunch of steps. And I imagined the first step would be parsing. I will have to parse and understand the file, what it actually contains. And I imagined that the output of this parsing would be a list of typed objects, so objects that each have a type and each have coordinates in the page. And then my job would be to map each object that I get from there to a composable, right? And also map the coordinates of each to a certain layout, right, in Compose. So this is how I imagine it would be like. However, it turned out this is not the common approach for actually rendering a PDF file in Android. It's much simpler than that. The way it would go is very similar, though. We still have the same input. We still have to do parsing. But the parsing result is different. It kind of combines those two final steps into one, which is just giving you a list of images. So for each page, it will just render an image file for you, like a bitmap, for you to show on the list. And that's why I said it's not a problem of PDF reading anymore, and more of how do you handle a list of zoomable images. Because what you will have to work with is actually images in the end. And the parsing is actually very easy. Now, that's easy and all, and it's very simple, but it comes with limitations, which is that image rendering in this way doesn't support the Karhes and linear stock features that we all know and love out of the box, And another name for these features is search and selection, right? It's a less common name, but so because it's an image, right, that we're showing, we lose context of what kind of content inside there is. It's just a bunch of pixels, right? And so that's kind of the limitation of image rendering this way. But luckily, there is a solution for this that we will see in a bit. Now, how do we even do the parsing, right? That's the first step. Luckily, Google this time actually did make something for this early in the days. Actually, since API 21, we had this API called PDF Renderer, which does the parsing for us. And it looks like this, how to use it. It's very simple. You just need to instantiate it, giving a file path, and then you open a page with a page index, and then you create a bitmap with the width and height that you want, and then you call page.render in this bitmap, which will create the actual data in the bitmap for you. And then once you're done with the page and the PDF render, then you just close both of them. So it's very simple to use. It also comes with solutions since API 35 for the limitation of image rendering. It introduced two APIs for that, search text and select content methods. Basically what they do is, for example, for search text, you give it this. By the way, this function is inside a page, so you call this from a page, right? So you call page.searchText, then you give it the text that you want to search for, right? What it does, it goes in whatever logic it has, and it gives you back a list of bounds. The list of bounds in the page, in the image, that actually match the text you're looking for. And so if you have the coordinates, the rectangles, right, then you can imagine, then you can do whatever you want with them. You can just draw some rectangles on top of the image, highlighting that part of the image that contains the text, right? It's a bit of a similar story with select content as well, where you just tell it where the user has started dragging their finger and where they ended dragging their finger, and that it will give you what that maps to as coordinates. And then if you have the coordinates and the rectangles, then you can just draw them as highlights in the image. So that kind of solves the problem. It's not really perfect because it's from API level 35, but still there is a solution there. So this is how the rendering would work, right? Now let's talk about zooming. And this section is going to be the meat of the talk. It's the most of the slides we have here. And when we talk about zooming, we talk about the zooming gesture, the pinch to zoom, right? So let's see how we can implement that. Let's imagine we have this lazy column, and we want to detect the zooming gesture on the lazy column. We can just add a modifier that is pointer input. And this one, in the scope of it, allows us to call this method detect transform gestures, which actually detects this kind of gestures. And it gives us 3 parameters that we can work with. First is a gesture centroid. What is that? When I zoom in with my 2 fingers, there's a point in between the fingers, right? And that's the point I'm actually zooming in on, right? So it gives me the coordinates of that point on the screen. And it gives me the pan parameter, which is how much I moved my finger across the screen, right? And it gives me the gesture zoom, which is like how much did I zoom in from the previous gesture to now, right? Is it like 100% twice and stuff like that? And based on that, I can basically update my zoom state, right? I can say zoom times the gesture zoom that I just did, and then I coerce it between two reasonable values for min and max. It's actually very simple to update the zoom state like this. But then we update the state, right? We need to apply that state somewhere. So how do we actually apply it? How do we actually zoom? And in Compose, there are only two ways to affect the size of a composable. We either do it in the layout phase or the draw phase. I just said them in reverse. But and in the draw phase, that's where we control how composables are drawn. In the layout phase, that's where we control how big they are and where we put them on the screen. And to control this in the draw phase, we will have to use the graphics layer modifier. And this allows us to set the scale X and scale Y fields, which actually makes it draw bigger than it actually is. But we need to understand that this is just about drawing. The bounds of the item is still the same. It's still in the same coordinates. The size itself didn't change, but the way we draw it on the screen has changed. So it looks bigger, but actually the size and bounds of it are not. Then there is a way to do it through the layout phase by using the size modifier. And we all know this. We just get the original page size and we just multiply it by the zoom state we have. And we can apply this either to the lazy column. So we can like zoom the whole lazy column, right? Or we can zoom on the items and then they will kind of push the lazy column with them, right? So seeing this, we kind of have like four ways of doing zooming. And not all of them are equivalent. They all come with their own pros and cons. So let's go through each one of them one by one and see how it actually works. Let's start with the draw phase applied to an item, right? So we have this modifier, and we have that list of random color boxes that I drew. And we're going to apply this modifier to this random color box composable. Let's see how it behaves when I zoom in. So you can see there's a gesture. I'm trying to zoom in. And you can see that as I zoom in further, the bounds kind of collide with each other of each box, right? And they're kind of zooming in, like zooming out and zooming in independently of each other, not like in tandem. The spacing is not respected and all that. So there is already a problem with this, that the items are not working together well. So this is not the way to go. Then let's maybe apply the draw phase on the lazy column, right? So apply this modifier on the lazy column as a whole. Let's see how that works. So I'm trying to zoom in, and actually it gives me the behavior I would expect, right, from a PDF reader or like a zoomable image list. So it looks good, but if I try to scroll, so I'm trying to scroll, and it does actually scroll, right? But if I try to scroll all the way up, I can see that there is an element like still there at the top, but I can't really scroll up to it, right? The reason for that is that the lazy column, from its point of view, it's already scrolled at the top. There is nothing more to scroll, right? It's just that the lazy column is bigger than the viewport through which I see the content, right? So when I scroll in the screen, it seems like I'm not to the end, but it's actually at the end of how much I can scroll. So this is one limitation of this way. Another limitation is, so let's see what happens here. So I'm zooming in, I'm zooming in, I'm zooming in, and I'm only left with two items that I actually see, but I can see that I'm actually composing more items than I'm seeing, right? And when zooming in on images, we're gonna actually increase the amount of pixels we're gonna render, right? That means the size of bitmaps we're gonna hold is gonna increase tremendously, actually. And if we are only seeing two pages, but we are rendering bitmaps very large for many more items, that's a waste of resource, right? We're gonna consume so much memory, and that's gonna draw the app performance down. So this is actually maybe the biggest limitation of this, because the other one, maybe we can hack ourselves around it some way, but this one is actually a fundamental issue. So the draw phase apparently is a no-go. It's not gonna work for us. Either we apply it on the item or the lazy column. Let's explore how it would look like on the item if we apply the layout phase on the item. So now, instead of the graphics layer modifier, we use the size modifier, right? However, in PDF pages, not all pages come in squares, and applying this will result in square pages. So we need to respect the aspect ratio of each page. And the way we can do that is by letting the page fill as much width as it wants, right? And applying an aspect ratio modifier as well. And here I'm just using some random aspect ratios, right? So let's see how this would behave if I zoom in. You can see I'm trying to zoom in, right? But it didn't really grow bigger. It grows smaller, but somehow it doesn't grow bigger. And the reason for that, and everything has a reason in this life, and also in Compose, is the composables. When they're composed and we try to lay them out, we get some constraints from the parent, and the top level parent is a screen, right? And that one has a max width, so it passes that along into the composable we need to lay out. And so when the composable sees that it has a max width, then it cannot exceed it by default. That's why it's not growing, but it's shrinking. Luckily, we can actually make it exceed this max width constraint by applying another modifier, which is called wrap content width. This allows it to take as much width as it likes without respecting the max width constraint. No need to delve into details about what these two parameters mean. They're quite simple to understand. And so this is how it would behave if we apply this, right? So now we can actually see that it is growing beyond the screen width, right? As you can see from the bounds there. Then in the previous approach with the draw phase, we saw that we're not disposing of items properly, right? When we are zoomed all the way in, they're still being composed. Let's see if we still have this problem. The way I tested this was by attaching a disposable effect to each item composable. And when onDispose is called, I'm going to print a logcat statement here. So let's see what happens. So I'm zooming in. I'm already disposing of 2 items, right, that were initially shown. Then I'm zooming out. A bunch of items are shown. Then all of them basically disappear, so they're getting disposed properly. And this way we can verify that we're actually doing the job correctly. So items are disposed. That's pretty good. And in the next slide, I wanted to show something else, which I forgot. I'm going to see it together. I honestly forgot what it is. Yes, it's an amount of recompositions that happen, right? So the more I zoom in, the more the more frequently I change the size, the more frequently I need to recompose the whole thing, right? And this may or may not cause performance issues, but there is. But if you're talking about a complex layout, maybe it does, right? And we want to limit all these variables if we can. And the reason this is recomposing is it's related to a post I shared both in the Android channel and in Framna Android channel at some point, which is that the page width is being read in the composition state, in the composition phase, right? So when it changes, it needs to recompose the whole thing. The way to fix this is by actually deferring the state read to the layout phase. So here I'm deferring that, and I can see that I'm zooming in without any recompositions happening, because the state change does not trigger a recomposition. And the only thing I changed here was using a lambda, passing a lambda instead of passing the actual parameter itself. And let's talk about how we can actually defer state reads. Unluckily, Google doesn't have this modifier with a lambda out of the box, so we have to create our own. I already shared the code in the channel, so you can find it easily. But if we want to go through it quickly, it's basically a layout modifier. It gets a measurable, which is our composable, and some constraints. And then we can get the width in pixels. And then we can copy those constraints that we get, and then we fix a specific width based on the one we get from the lambda parameter. So by setting the min width and max width to the same value, we're essentially setting a specific width that we want, right? So we update the target constraints, then we measure with those target constraints that we created, and then we lay out the item. It's very simple. It's as simple as that, actually. So that was the zooming, how we can actually increase the size and zoom and everything. But as you can see in the examples, but maybe even clearer here, so you can see in the video that I'm going to zoom in the middle of the screen. So I'm expecting that the point in the middle is going to be the one in focus when I keep zooming in, right? But let's see what happens here. I'm zooming in, but it seems like it's zooming in on another point, right? Let's understand why that happens. So the zooming is not centering on one point. And to understand how it happens, I took this image, random image from the internet, and I put this dot, which represents where I'm going to zoom in, right? And then I'm going to animate how it evolves as I increase the size of the image. And remember, we're increasing from this point, right? This is our transform origin. So things increase this way in Android coordinate system. Let's see how it evolves. So first of all, it doesn't even stay at the same point, right? That's already understood. What's the difference, though? We can see that it got pushed to the right and also pushed down. And the reason for this is actually simple. Basically, we're zooming in, and what zooming in means is that for every pixel, we're kind of representing it in a bigger amount of pixels, right? So all the content above it and to the left of it is being increasing in size, and so it pushes it down and it pushes it right. And so if we want to keep it in focus, we need to understand the difference between the previous and the next state of the zooming, and kind of offset that back, correct the value, so that we can always keep it in the same place. So we have to keep translating it back to the same place by the amount it changed all the time. All the time there's a gesture. How can we do that, right? So going back to this modifier that we wrote for increasing the zoom, we can make some changes. And that's by using a translation X state. This will allow us to correct the state on the horizontal axis. And basically what we do here in this calculation, you don't have to pay too much attention to it, but we're just taking the difference between the next and previous coordinate of the gesture centroid and applying that as a translation to make it go back to where it was. That's basically the principle here. And we apply the state of translation X to the graphics layer modifier. Now, we saw earlier that the graphics layer modifier doesn't work, right? But that's only because we applied it on a vertical list of items. But right now we're applying this to an item that doesn't have anything left or right to it. So there's only it on the horizontal axis, right? So we won't hit any recomposition issues or items not being disposed at the right time or anything like that. And so we corrected the horizontal axis. Let's correct the vertical axis. So the same way we translate, we're going to scroll. And we're already in a scrollable list, right? So that's why we don't need to go through the graphics layer modifier. We can just scroll on the lazy column. And it's the same calculation. We're taking the difference between the now and then, the gesture centroid coordinate, and we're applying it as a scroll. But unfortunately, that's not enough. There's something missing here, which is when you zoom in and you increase the sizes of items, there is this stuff that's displayed on the screen, but there is also sometimes items that extend above the screen because they're not all gone, right? Some of it is showing in the screen, and some of it is showing outside the screen, right? But because it belongs to the same item, then it's also increasing in size. So even the stuff above the screen that's being clipped is also increasing in size and pushing down on the content in the screen. So we need to take that into account, and that thankfully list say does give us how much offset is the first item, and we can just apply that directly. Now applying this will result in this kind of result. So you can see on the before on the left and after on the right, and how accurate the zooming has changed, right? We can even scroll and change the point. It's going to work the same way. Okay, so this was the biggest section in the talk. Now, let's talk about panning. And with panning, we're still going to use the same function that we used earlier. It's just that we want to pan when there is no zooming happening. So we're going to have a condition. So if we are zooming, if the gesture zoom is different than 1, then we're going to, so if it is zooming, then we're going to apply the zooming logic. If it's not zooming, then we're going to apply the pan parameter that we get. And that's how much the user has moved their finger, right? We're going to apply it to the translation X state that we just saw. And we're also going to scroll by that amount. So we can also scroll vertically and horizontally at the same time. But I found that if I'm zoomed in a lot, then if I pan by the same amount I move my finger, it's not really enough, because I'm zoomed in so much that all the elements are much bigger than they used to be, and my finger movement is too little. And if I want to move from the end of the text to the start of the text, it takes me like too many swipes, right? So I want to increase the speed of my swipes. And I just randomly tried applying the square root of zoom, and it actually just worked in the so from my own personal experience, applying the square root of zoom just makes the speed at it scales with zooming, but doesn't scale linearly, because the square root, from your perspective, the curve would look like this, right? So it doesn't like keep going like this, and that will keep it at a reasonable speed, that it doesn't like fly all over the place, but it kind of is reasonable for you to follow with your eyes. And that was the panning. So the panning was actually quite simple. So we finished the 3 main features, right? The rendering, the zooming, and the panning. Now, let's talk about optimizations and enhancements. Because just applying that resulted in my phone almost exploding of heat, right? There's so many things happening all at once when rendering bitmaps that it just makes the phone heat up so much and eat so much resources. So how can we optimize that? First thing first, the low-hanging fruit is to recycle our image objects, which are the bitmaps, right? So if an item goes out of the screen and is disposed, then we should recycle the bitmap it was using. Then we need to apply a technique of incremental bitmap zooming. So when the user zooms in, doesn't mean that we need to increase our bitmap size or our image size. We need to show the user that something's happening. So we're increasing the size of our composable, but the image asset itself, we're not asking for a bigger one just yet. We wait until the user has finished interacting with the screen and has settled on a particular zoom level, and then we ask for a bigger image with a high resolution so we can actually show it to the user. And that's kind of explains the effect of sometimes you see when you zoom in, things are blurry, and then they become not blurry, right? They become more sharp. This is actually what's happening. And you can apply some kind of duration where you wait and see if the user has finished. I just applied 200 milliseconds as the arbitrary value. And part of this as well is if the user, let's say, zoomed in 2.1, right, from the original size, we can ask for an image of 2.1. But then how about they just wanted to see a bit more? So they increased to 2.3, right? So we're going to ask for 2.3. The way something I came up with was to just have zoom buckets. And my zoom buckets are like go in increments of 0.5. So if they zoomed in at 2.1, I'm going to ask for an image of 2.5. And if they zoom in a bit more, I don't have to create a new image. I already have a zoom bucket that applies to it, right? And this way, I minimize the amount of time I need to render a new bigger image, and using the CPU, and the amount of time or the amount of memory I need to take as well, because it's still the same image. Then we can also apply an optimization, which is caching the images we actually render. So instead of asking for them on the fly all the time, we can just cache them on disk, and that way we will use less CPU, and it's going to be faster actually for bigger zoom levels. And one last thing is, and this is something I recently found out about, is when you render a bitmap, you can choose to render it with this kind of hardware config. And I'm gonna talk about why it's beneficial in a bit, but basically what it does, it reduces the app memory footprint, and it results in fast drawing performance. I didn't understand what this is to begin with in the beginning, so I asked around the internet, and apparently, when you draw a bitmap on the screen, what happens is the bitmap data is copied over to the GPU, and then it's held in the GPU memory, and then the GPU can then draw it on the screen. What this allows to happen is to skip that copying phase. It just puts the image to begin with in the GPU memory. So you don't have to actually copy it. So that reduces the amount it takes to draw, because it's already there in the memory next to the GPU. And it reduces the app memory footprint, because now the image doesn't live in your own app space. It lives in the GPU space, right? That's basically what it does. And the reason I put maybe use it is when it first got introduced, I think it was in 2017, and I saw some threads in Stack Overflow about people complaining about what if the GPU memory is now overflowing? What happens then? And people didn't really know what's going to happen. So there was some question marks around it, but this was from 2017. I'm pretty sure they made some improvements, but honestly, the documentation doesn't say too much about this, so I'm not really sure. So you have to try it on your own risk.
I think in general, it tends to overflow to the system memory, and then it overflows to virtual memory, just a disk.
Okay, and some people also said that if it doesn't find memory to allocate the image to, it just returns null or just fails the operation. So you can test around
it.
that.
Could be that they made it differently than most other architectures, but usually that's the way it goes.
Okay. Then let's move on to enhancements. And one enhancement I could think about was disabling the scrolling on a lazy column when we're trying to zoom in, because I found out that when I put my two fingers on the screen and I'm trying to zoom in, if I put one finger first and maybe it moves slightly, then the lazy column starts scrolling and it kind of overtakes all the next touch gestures. So even if I put my second finger on, it's not going to do anything, because the lazy column, the list, is kind of just doing its own thing now. So one way to avoid this is if we detect that there are two fingers on the screen, then just disable the user scrolling on the lazy column. And then another one is just to double tap to zoom. There is also a modifier, or not a modifier, like a function in the pointer input modifier that we can call, and which will detect this for us automatically. And we can actually just reuse the code that we had in the other function. And that's basically it. Yeah, thank you for your attention.